So a conservative force allows conversion between your kinetic and potential energy. Gravity and spring force are conservative. The work done between 2 points by any conservative force can be expressed in terms of a potential energy function, and it is reversible. It is independent of the path between the 2 points, and is zero if the starting and ending points are the same. A force such as your friction that is non-conservative is called a non-conservative force or a dissipative force. So you have observed that your kinetic and then your potential energy are not anymore conserved when you have your work other, such as your work of friction. But here again, your energy is, your total mechanical energy of your system is conserved. It's just that your kinetic and potential has been converted to some thermal energy in the form of your friction. So those are your conservative and non-conservative forces. So non-conservative forces do not store potential energy, but they do change the internal energy of a system. The law of conservation of energy means that energy is never created nor destroyed. It only changes in form. Thus, this law can be expressed as your delta K plus delta U internal is equal to 0. Your internal energy, this one here, you're going to learn more about this one on your thermodynamics class. So later you're going to extend now your conservation of energy to thermodynamics. Okay, so by the way, what you can see here on the GIF or on the video is being confident that you're not going to be hit by the metal ball. Because if you're going to start at this specific point, like say for example at this point here, okay, due to the conservation of energy theorem, it will always end up at this point here when it turns to use. It will never go higher than that unless there is a net external force, such as if you're going to push harder from the other side, so it will hit your head. But here you're confident enough that it will not hit you. Okay. So let's have the last example, and this is an interesting one. Okay, so a 15-kilogram stone slides down a snow-covered hill, leaving point A with a speed of 10 meters per second. There is no friction on the hill between the points A and B, but there is friction on the level ground at the bottom of the hill between B and the wall. So let's just analyze the situation. So you have here a stone at the top at point A, which slides down a snow-covered hill. So snow-covered, so this means here that this is frictionless. Okay. But there is friction on the level ground at the bottom of the hill between B and the wall. So this one here is your wall. And this is a rough surface here. Okay. After entering the horizontal region, so after this one here, from point A, your stone slides down towards point B. So it slides down towards point B. And after entering the rough horizontal region, the stone travels 100 meters. Okay, so it travels at this one here. It travels this point here. This is 100 meters. And then runs into a very long light spring with force constant of 2 newtons per meter. So after the stone has traveled 100 meters, it interacts with a spring. So this one here, this is a spring. Okay, which has a force constant of 2 newtons per meter. And by the way, the spring is very light and very long. The coefficients of kinetic and static friction between the stone and the horizontal ground are 0.20, your coefficient of kinetic friction, and 0.80, your coefficient of static friction, respectively. For the problems, what is the speed of the stone when it reaches point B? How far will the stone compress the spring? And will the stone move again after it has been stopped by the spring? So let's just review again the problem. So for the problem, you have here a stone at point A, and then because you have your force due to gravity, it slides down towards the snow-covered hill. Snow-covered, so meaning this is frictionless. Okay, and after it has entered point B, or once it reaches this point here at point B, it travels 100 meters on a rough horizontal surface. And after traveling 100 meters, the stone meets a spring, which is very light and very long. And of course, you know that because the stone is traveling here, you know that it can compress the spring at some point. Okay, so the stone will compress the spring at some point here. Okay, so from point A, it slides down, travels this horizontal surface, meets a spring, and then it compresses the spring. So for our problems, what is the speed of a stone when it reaches point B? What is the speed? What is the speed at this point here? So we're asked of the speed here. And how far will the stone compress the spring? So at this point here, we are asked of the x compression. And will the stone move again after it has been stopped by the spring? So the spring acts like a stopper. But of course, your stone will not be attached to the stone is not attached to the spring. So it might be that later at time t, that that it might be possible that the spring can do work on your stone and it can push it back, or it might be also that the stone and the spring will stick together. So let's see later which of the following situation can work on your system. So let's solve the problem. Okay. The first thing that I like to do is to divide or to break down the situation into parts. So let's do this. First, let's label some points. At point A, let's say that this is your event 1. At point B, at the ground, that is your event 2. And then at point 3, when you are now going to compress the spring, that is your point 3. Okay, and then we take the level ground to be your y equals 0. So at this point here. And we can divide the system into 3 parts. Okay, we can do it by dividing this one here. So from point 1 to point 2, and then from point 2 to point 3. So our first target is the velocity at point B or at event 2. So our target here is your V2. That is the speed here. So solving the problem, we just use your energy conservation. You have your E1 is equal to your E2. Since we are only concerned with the speed here at the bottom of the hill, so let's take this subdivision in the solving of the problem. So we just use this event here and just disregard first your event from point 2 to point 3. And at this point here, you only have your gravitational potential energy. So there is no spring around here. So that means your energy conservation becomes your K1 plus U grav 1 plus work other. This is equal to K2 plus U gravity 2. But this one here is frictionless. So we do not care about any friction. So your work other is just 0. So we just have your K1 plus U grav 1 is equal to K2 plus U grav 2. Okay. However, we can still cancel some terms. At point B here, so at point B here, or at point 2, your Y now is equal to 0. So you do not have any more potential energy here. So since we do not have any more potential energy here, your U grav 2 goes to 0. So we just have your K1 plus U grav 1 is equal to K2. By the way, point 1, you have your velocity 1, which is equal to 10 meters per second. So your stone leaves point A with a speed of 10 meters per second. Okay, so from that, we have your 1/2 mv1 squared plus mgy1, which is equal to 1/2 mv2 squared. Our target variable again is your v2. Okay, so next we have, let's solve the problem. Here you have your y1 is equal to 20 meters. Your v1 is equal to 10 meters. So that's 10 meters. As 10 meters per second, sorry. So again, you have your 10 meters per second. So solving the problem, you have again 1/2 mv1 squared plus mgy1 and 1/2 mv2 squared. So you can substitute these values to your equation also with your mass of your stone. The mass of your stone again is equal to 15 kilograms. And substituting the values for your kinetic energy 1, you have 750 joules plus your potential energy 2, you have 2940 joules. This is equal to 1/2 mv2 squared. Our target is your v2. So that means you have to multiply both sides by 2 and then divide by m. So you have 2 times 3690 joules. You have 750 plus 2940, that is 3690 joules, divided by the mass m, so that you have your v2. But this is a squared here, so you get the square of both sides, square it on both sides, then you have there your v2. And again, this has a positive and then a negative root, but your stone moves to the right. So we're going to choose the positive root. So here, your v2 is equal to 22.2 meters per second. So that is the speed of the stone at point B. That is also the speed in which the stone will move from point B up to the spring, which later it will compress. Okay, so we have already solved your velocity at point B, the speed at which the stone will use to travel on the rough horizontal surface towards the spring, which later on it will compress. So just a quick review. We have divided your event or your problem into 3 events. You have event 1 at the top of the hill, event 2 at the bottom of the hill, and then event 3 the time wherein the spring will be compressed by the stone. So our next target is to find uh, uh, the compression or the compression x. The target is the compression displacement x3 at this point here. Okay, because we were asked of how far will the stone compress the spring. So our target is your x3, the displacement in which your spring will be compressed at some distance. So our target here is x3. So we have again for this problem, we are going to take this fraction of the problem. So we're going to look into from point 1, sorry, we're going to look into from point 2 to point 3. So here, at this point here, this is now friction. It already contains some friction here. And this is at the level ground, y equals 0. So that means here, at this point here, we do not have any more your gravitational potential energy. But here we have your spring. So instead, you have your elastic potential energy for your spring. So from your energy conservation theorem, you have your E1 is equal to E2. Sorry. For us to be not confused, let's use now your E2 to E3. Okay, so we have K2 plus U elastic 2 plus work other. This is equal to K3 plus U elastic 3. Let's cancel some terms. Okay. So one thing that we can cancel here is here at point B. If you're going to look at point B here, there is no spring here, right? No spring at point B. So since there is no spring at point B, your U elastic 2 goes to 0, since you do not have anything there that is stretched or compressed. Another thing that we can cancel is at this point here, at point 3. So at point 3, when you have your maximum compress, or at the point when your spring is compressed, your velocity 3 is 0. So because we're asked of how far the spring was compressed, so that means that is the time wherein the stone already stopped moving or stop compressing your spring. So that means your K3 is 0, since we do not have your velocity at that point. So we just have your K2 plus your work other, and then you have this is equal to U elastic 3. Okay, so your work other is due to your friction. So let's write some terms. You have 1/2 mv2 squared plus, or since this is a your friction is a non-conservative force, you have your minus Fs. Of course here that is minus Fs because your displacement is to the right, but your friction force is to the left. So it restricts your movement. So you have your minus Fs. So the work done here the work done, the work other here is equal to negative Fs, where F is your friction, S is your displacement, and then this is equal to 1 half kx3 squared. Our target is your x3, the maximum or the compressed state of your spring. By the way, what is S? What is your displacement S of your stone? Or what is the work done by the S? What is the displacement S for your friction? So here we have, let me erase some terms. Let me erase this one here. So if you can see, if you can remember, the stone travels 100 meters up to here, right? It travels 100 meters. But then it does not stop there. So it travels at least some point here up to your spring will be compressed. So let's say that this is here, but again, this is here, it's just your X3, right? This is your compression of your spring. And even up to this point here, you still have your friction. So that means your S is, you have your 100 meters plus x3. Okay? So if that is the case, we have we have then now your 1 half m 1 half m v2 squared minus, for your friction, if you can remember, that is just your since it is moving, you have your mu k n, your normal, or this is equal to mu k mass times your gravity. So you have your mu k mg s. Let's move your 1 half kx3 squared to the left. So you have your 1 half k x3 squared, and then this is equal to 0. Okay, so please see the next slide. Let's move to the next slide for our next solution. So we ended up with this equation. You have your 1 half mv2 squared minus mu k mgs minus 1 half kx3 squared. This is equal to 0. And you can solve this one. Your 1 half mv2 squared, your kinetic energy 2, this is equal to 3690 joules. And then your, again, your S is equal to 100 meters plus your x3. Your mu k, this term here, your mu k mg, this is equal to, this is minus 29.4 times S, which is 100 meters plus x3. And you have your 1 half times k, your k is equal to 2 newtons per meter. So this is just minus x3. That is equal to 0. Simplifying further, you have 3690 joules minus 2940 joules minus 29.4 x3 minus x3. This is still squared, sorry, this is squared. Is equal to 0. 3690 joules minus 2940 joules, that is equal to 750 joules. minus 29.4 x3 minus x3 squared. This is equal to 0. Let me just rewrite this function. So we have x3 squared plus 29.4 x3 minus 750 joules. This is equal to 0. So I just rewritten your equation to this form, but these are just similar terms. And as you can see here, you have your x3 squared and then another x3 here. This is actually a quadratic function. Okay, a function wherein you have your x squared and then another x. So you can solve this one using you can solve x using your quadratic function. So solve x using your quadratic function. Okay. So I'll leave it to you to solve the problem using your quadratic function, but you can you'll get two answers for that, and you're going to use the positive answer for your x3. So solving that one using the quadratic function, you get an x3, which is equal to 16.4 meters. That is the compression of your spring. So that means here that your stone actually traveled 100 meters plus 16.4 meters along the rough horizontal surface. So again, I'll just leave it to you to solve this function using the quadratic formula. Solve it using the quadratic. Solve this one using the quadratic formula. Okay. So finally, we're down to the last problem. So will the stone move again after it has been stopped by the spring? So we're just going to look at the problem at this point here. Okay. So let's just write some notes. So after the spring is compressed, okay, after the spring is compressed, of course, the stone will have a velocity that is equal to 0, so meaning it stops. So once it stops, so in order for the stone to move again, so in order for it to move again, your elastic force should be greater than your static friction, because I've said, if you can remember from our previous discussion, you need to overcome the elastic or the static friction so that you can start to move a thing. Okay, so if you can remember, the static friction is greater than your kinetic friction, and you need to overcome this static friction so that you can move your system. And if the system is already moving, you'll now have only your kinetic friction acting on your system. So when applying some force F, your force F should be greater than your elastic frictions so that you can move a thing. Like say for example, when you're going to push a table, the force that you apply on pushing the table should be greater than your static friction. Otherwise, if you're only going to apply a small force, you cannot exceed your static friction, thus the table will not move. So in this case here, since the force that will make the stone to move again is your elastic friction, your elastic force. So your elastic force should be greater than your static friction. Now let's solve first your elastic force. So this is just your kx, okay, And we have solved your you have your K, 2 newtons per meter, times your X3, which is equal to 16.4. So your force elastic is equal to 32.8 newtons. Now let's solve for your static friction. So for your static friction, this is equal to mu s n, or mu smg, and then this is equal to 0.80 times 15 kilograms times 9.80 meters per second squared. So your static friction is equal to 118 Newton. Okay, so what do we have here? Your static friction, your Fs is way much greater than your F elastic. So that means here that the spring was not able to move, uh, to make the stone move again. So that means here the stone will get stuck with the spring. So there is forever for the two. If instead that the force elastic was greater than the from your static friction, then the stone will move back again. So it will perhaps move some distance there, some displacement there, and that is when you say that you have your pinagtagpo pero di tinadhana. So in this case here, we have the spring and then your stone getting stuck together forever. Joke. So that's it. So this ends lesson 7. So I hope that you learned something from this lesson. And in the next lesson, we're going to discuss about momentum, impulse, and collisions. So that ends our lesson. May the force be with you. Thank you for listening.